Working through the ice table worksheet. First of all, you need to set up an ice table. It's very important that you can read the problem and put the information where it goes. Initial pressures, so we're working on the I line. 1 atmosphere NO. So that's 1.000 atmosphere and 1 atmosphere oxygen. And I'm going to quit writing atmosphere in it because it gets kind of bunglesome. At equilibrium, so I'm on the E line, the partial pressure of oxygen is 0.506. Okay? So I know if I start with 1 atmosphere of oxygen and I end with 0.506 of oxygen, I know that I had to use oxygen. So I'm going to put a negative on the change line. Okay? If I'm using oxygen, then I also must be using NO. If I am using reactants, then I must be making products. It will always work this way, in that you will either always use reactants and make products, or you will always use products and make reactants. Okay, so one side of it will always be completely negative and one side positive. You can't be using and making reactants at the same time. Now, if I start with 1 and I end with 0.506, then by subtraction, I can figure out how much I used. I used 0.494, the difference between 1 and 0.506. Now, remember, there's something really special about this change line, and only this line. The ratio on this line has to follow the stoichiometry of the reaction. Y'all, that does not happen on the initial line. That does not happen on the equilibrium line. But what you're using and what you're making must follow the stoichiometry of the reaction only on the change line. In other words, if you can see this balanced equation is 2, 1, and 2. That means the ratio of these numbers on this line have to match that. So if oxygen's number, as you can see, is 0.494, then that means the NO number must be twice that, because its coefficient is twice that of oxygen. So that number is 0.988. Okay? The coefficient of NO and the coefficient of NO2 are the same. Therefore, the number on the change line will be the same. And from here, we just do the math, okay? And something I didn't say early on this one, but I think I pointed it out when we were initially learning ice tables. When the problem doesn't give us an amount of NO2, or if it doesn't give you an amount of something, you assume you're starting with 0 of that, okay? So I finish out this math, and I get 0.012 and 0.988. And we know those are all in atmospheres, okay, because I left off the units. There are 2 things I have to calculate here, a Kp and a Kc. Both of these are equilibrium constants. Kp is when you are using pressures. So this is going to be a Kp because I'm using atmospheres. Now, we know that to calculate this equilibrium constant, we need the products over reactants raised to the power of the coefficient. So we need the pressure of NO2 squared divided by the pressure of NO squared times the pressure of O2. And that's raised to the first power. The exponents, again, are the coefficients. So then I'm going to plug in my equilibrium numbers. And since equilibrium constants, the numbers are unitless, all I have to worry about here is that I'm plugging in atmospheres. I don't have to actually put the atmospheres in the equation. Watch the math on it. For Kp, I'm getting 1.34 times 10 to the 4th, okay? Again, unitless. The other thing it asked me to calculate it is a Kc. to calculate a Kc, I have to use concentration. C is for concentration, which would be molarity. And there's a formula that allows us to convert between Kp and Kc, and that's this, that the Kp is equal to Kc times the RT raised to the delta N power. This formula is in your book in section 15.3, I believe. But this is the formula. So the Kp is this number, 1.34 times 10 to the 4. The Kc is what we're solving for. R is the ideal gas constant, which we learned when we dealt with gases, 0.0821 liter atmosphere per mole Kelvin. T is the temperature. I have to put that in Kelvin. It's in the problem, 184 degrees Celsius, and I'll convert that to Kelvin. Delta N, you know delta means change in, the triangle, change in, and N is moles. So we need to, when we measure a change in something, it's always the final minus initial. And so we look at our balanced equation. The total mole, the final is the product. The total moles of gaseous product is 2. I'm getting that from the coefficient. The initial, so it's final minus initial. The initial is the reactant. So the total moles of gaseous product is 2 minus the total moles of the gas reactants is 3. So my delta N is going to be -1. And now I'm going to plug those numbers into the equation. Delta T. You should remember how to convert Celsius to Kelvin. Now notice in the math of this that the only thing raised to the -1 power is what's in parentheses, okay? And I'll solve for that. .0821 times 457, I get, for this math, 37.5 such and such, okay? I raise it to the -1 power, and when I do that, I got 0.02665, etc. And then I take the 1.34 times 10 to the 4, divide it by 0.0265, and so my answer for the Kc is 5.03 times 10 to the 5th. And again, that is unitless. Okay, and that's number 1. Okay, number 2 on the worksheet. Again, take a minute and set up your ice table and see if you can set it up yourself, and then play the video and make sure it's set up the way that it's supposed to be. Okay, so this is putting moles into the ice table. Now, you should always put moles or atmospheres in an ice table, not molarity. But you know that when you calculate the equilibrium constant, products over reactants raised to the power of the coefficient, that has to be the molarity, the concentrations. Do you remember how to get from moles to molarity? You should. Molarity is moles per liter. So to convert these to molarity, I'm going to have to divide them by the total volume. That actually is really easy in this problem because the total volume is 1 liter. So the moles and the molarity are the same number. Now, this problem is different. It wants to know what is the concentration of water at equilibrium, and it gives us an equilibrium constant. Well, we know that the equilibrium constant, 0.26, is equal to products the concentrations over reactants raised to the power of the coefficient. Okay, remember that square brackets would mean concentration. Okay, so I'm going to cross multiply and solve for the concentration of water. So I get that the concentration is 0.0184. That would be molarity. Okay, the equilibrium constant doesn't have units, but the concentration of water does have units. Okay. Now, try to work number 3 on your own. So pause the video, work number 3 on the worksheet, and then play the video to check your answer. I often say this, you can watch me work problems all day long, but until you try to work them yourself, you're not going to know if you can do it or not. So pause it and work it yourself. Okay. So, iodine is I2. Iodide is the ion, I negative. It's important that we can connect the names in the formulas. And so we're starting with 1 times 10 to the minus 3 iodine and 1 times 10 to the minus 3 iodide. We're not told anything about this I3 ion, so we'll assume it's 0. And then we're told that the iodine, the I2 at equilibrium, is 6.61 times 10 to the minus 4. So by subtraction, we can figure out the change. And obviously we're starting with more than we started with, so we know that we're going to be using reactants and making products because it makes sense. You can't start with 0 on the product side and use some of that. You're not going to have negative equilibrium numbers. Okay. The stoichiometry of this reaction is 1, 1, 1. So that means I'm going to have the same number all the way across on the equilibrium line. Then I'll say 1 times 10 to the minus 3 minus 3.39 times 10 to the minus 4. I might should have rewritten this so that things aren't so bungled up. And then to calculate the Kc, I will say products over reactants, and for shorthand, instead of writing 6.61 times 10 to the minus 4 times 6.61 times 10 to the minus 4, I'm just going to write it like so. And for my answer for Kc, did you guys get 776? Again, it's unitless. Okay, number 4. We're given an equilibrium constant. Okay, so we're told that the Kc is 24. We're given a temperature in Kelvin, and we're told that the starting concentrations of cystolbene is 0.850 molar. And that is all we're told. We are asked to determine the equilibrium concentrations, and so this is what we want to know. Okay, not given a lot of information. We can assume that since we're not told anything about the trans-stilbene, that we are starting with 0. And we know that if we're starting with the cis and we don't have any trans to start with, we know that this reaction is going to proceed from left to right to reach equilibrium. In other words, we're going to use the cis and make the trans. So the reactant side is going to be negative, the product side is going to be positive. We don't know a number for how much we're going to use, but we do know the stoichiometry of this reaction is 1 to 1. So therefore, we know we're going to use X amount over here on the reactant side, and we're going to produce X amount on the product side. Okay? That means at equilibrium, our numbers will be 0.850 minus X on the reactant side, and the product will be 0 plus X, and I'm not going to put the 0 in there because it just complicates things, the look of them. I'm just going to write X. And so if Kc is 24, I know that 24 is equal to products over reactants raised to the power of the coefficient. So the products and the reactants are all a 1 coefficient. So the first thing I'm going to do is I'm going to cross multiply. So, and I have to distribute the 24 times the 0.85. It's going to be 20.4, and then the 24 times the X is going to be 24X. And then I'm doing this, right? I'm cross multiplying. It's equal to X, and I'm going to get all my X's on both sides. So for X, I get 0.816. So I'm not finished yet because the equilibrium concentration of trans-stilbene, that's X. It's 0.816 molar. But the cis-stilbene, I have to plug that in, and it's 0.034 molar. Okay, number 5. Set up your ice table and enter your information from your product, from your word problem. Okay, the Kc is 54.3. I want to know what are the concentrations at equilibrium. If the initial concentration of both hydrogen and iodine, so I'm starting with 0.240 of hydrogen and 0.240 of iodine. Okay, I know that means that's all it tells me, so I'm not starting with any HI. In terms of X's, what's going to happen here? Watch the stoichiometry. Do you agree that we've got to use the hydrogen and make the HI? That's the only thing we can do. We're only starting with reactants. We're not starting with any products, so we have to use reactants, make products. We don't have anything about numbers here, so I know I'm going to use X of each reactant because the coefficients are 1 and 1, and I'm going to make 2X of the products. That means at equilibrium, I'm going to have 0.240 minus X for hydrogen, 0.240 minus X for iodine, and 2X for HI. So my Kc, which is 54.3, is equal to products over reactants raised to the power of the coefficient. I have to square the 2X because there's a 2 coefficient. The reactants, it's 0.24 minus X times 0.24 minus X. So I'm going to say 0.24 minus X squared. Okay? The first step, what you're going to want to do here, you're not going to want to multiply this out and do FOIL, and etc., because that'll lead to quadratic equations. So what you need to do is square root both sides first. So when I do that, I get 7.36, some numbers, equals 2X over 0.24 minus X. It just gets rid of the square, okay? From this point, I do exactly what I did before. Cross multiply, like I did on the previous problem. And now when I punch in this in my calculator, I'm not entering 7.369 times 0.24. I've got the number still in my calculator, 7.368853371, okay? I'm telling you that because my numbers, if you round, you're going to get different numbers than what I get. x, I get 0.189. Again, that's just the answer for x. To answer the question, I have to plug the x in. And so the concentration of hydrogen, I get 0.051 molar. Iodine is 0.051 molar. And HI is 0.378 molar. Okay, now for number 6, I'm going to give you limited information on this one, okay? To see if you can, I'll give you the final answer. But it's the same problem, but it gives you different numbers, okay? So really it's just a challenge of your math skills, if you will, okay? It gives you different numbers, and it gives them in terms of atmospheres. So that means we need a KP instead of a KC. All right, we go back to this formula. KP is equal to KC times RT raised to the delta N power. We have a temperature, okay? We know what R is. What's the delta N? It's the total moles of gaseous products, which is 2, minus the total moles of gaseous reactants, which is 2. And so 2 minus 2 is 0. So that means the delta N is 0. Anything raised to the 0 power is 1. So that means that the KP is equal to the KC. So the KP is still 54.3, just like it was in problem 5. Okay? When I cross multiply and I get down on this problem to solve for x, I got that x is 4.52. I'll plug that back into my concentration for my hydrogen and my iodine. I'm intentionally not doing all the work because I trust that y'all can do that based on looking at what we did for number 5. And that means the equilibrium concentration of hydrogen, because I'm going to have to subtract it, is going to be 1.23 atmospheres. The equilibrium concentration of iodine is also going to be 1.23 atmospheres. And the equilibrium concentration of HI is going to be 2 times X. So it should be 9.04 atmospheres.